In the last lecture, we started our discussion on radiative transfer in gases. We saw that because gases absorb radiation, they can also scatter radiation. The directional spectral intensity in a gas is not a constant, it changes. And we saw that a simple expression relates the change to the incoming intensity, the thickness of the layer, and a constant of proportionality called the extinction coefficient. The extinction coefficient has two parts, the absorption coefficient and the scattering coefficient. So, what this equation says is that the number of photons going in a given direction is reduced, the minus sign here, is reduced by either absorption or scattering. So, in the initial lectures, we will focus only on absorption. So, we will look at a non-scattering medium. To simplify the discussion, and we add scattering later. So, in a non-scattering medium, you see that the rate of change of intensity with x is nothing but minus a lambda I prime lambda. This is a simple first order differential equation, and all of you can solve it, and the solution will say that I prime lambda at any x is equal to I prime lambda at the origin into e to the power of minus a lambda x, if a lambda is a constant, a lambda is not varying along the x. Okay. And so, you can see that a lambda has to have the units of 1 over length, and 1 over a lambda can be thought of as the photon mean free path. That is, it is the average distance that a photon travels at that wavelength before it is absorbed. So, it has a lot of similarity to the concept of molecular mean free path, which most of you are aware from kinetic theory. So, this is an important quantity, and you can also imagine if you have a gas layer of dimension L, a lambda L, if it is much greater than 1, we call it a thick, optically thick medium. That is, it is highly absorbing, because you can see that if you put a lambda L here, this quantity will become very small. There is a very rapid attenuation of the radiation. On the other hand, if a lambda is much less than 1, we call it optically thin. So, there is hardly any attenuation of the radiation. Now, we can also look upon this as a lambda L much greater than 1 is equivalent to saying that length of the medium compared to the photon mean free path is much greater than 1. That is, the medium is much larger than the typical mean free path of the photon. And in the optically thin limit, the length is small compared to photon mean free path. So, you can see that the way radiation will behave in the thick limit and in the thin limit will be very, very different. So, let us take again this gas of length L. So, the photon which is emitted by this surface 1 will not reach 2 at all if it is a thick limit, because the photon is very quickly absorbed right here, and the gas may emit another photon here which will travel again a short distance. So, the surface 2 here will not actually see radiation emitted by surface 1, but merely will be only looking at those photons which are within a distance Lp of this layer. So, you can imagine that this situation, the radiative heat flux arriving at this surface is controlled by what is happening in this region and is independent of that region. On the other hand, if the thin limit, then the photon will travel from almost 1 to 2 without much attenuation. So, 1 and 2 will see each other, and this is the case that we really covered earlier when we neglected absorption by the medium between two surfaces. We assume that the radiation leaving this surface is equal to that arriving at this surface. So, that is valid in the limit when this quantity is very small. Now, the very unusual differences of behavior in the thick and thin limit is very important to understand the problem in real world situations. Now, this is also complicated by the fact that A lambda varies strongly with lambda. So, as you vary the wavelength, this A lambda will fluctuate in a wild way. Let me give you a sort of a qualitative picture here. Suppose you plot A lambda with lambda for a typical gas, it will have wild variations. Okay. And so, it will go from very high value to very low value over a very short distance. So, the same gas can have A lambda L much greater than 1 at 1 lambda and A lambda L much less than 1 at another nearby lambda. So, the gas behavior is very different at two adjacent locations like this and this. Here it is optically thin, here it is optically thick. So, this is the real challenge we face in radiation heat transfer. The fact that the absorption coefficient in most gases is a very complex function of lambda, rapidly varying with lambda. So, if you want to make any approximation such as the thick or the thin limit, you got to be very, very careful, because in examples in engineering, there are very few situations in which you can really apply one of the two limits. These limits are useful as a pedantic tool to understand the behavior of gases, but real gases have such complex dependence of the absorption coefficient with wavelength that the they may simultaneously be in the both thin and the thick limit, depending on which wavelength they are looking at. So, this issue we will keep repeating and reiterating, because this is the fundamental problem in solving radiative heat transfer problems in gases, because in contrast to liquids and solids, whose emissivity and absorptivity behave in a somewhat smoother fashion, in the case of gases, the spectral variation of absorbed coefficient is very, very strong. And let me make this point more clear, which we had mentioned in the last class. I'll repeat it. If you look at what is the emissivity or absorptivity of a gas, you look at the intensity, and we just redo that. You want the intensity at the surface minus intensity at distance L away, divide by the intensity at 0. This is the directional spectral absorptivity of the gas. So, this is the attenuation, this is divided by the initial intensity, this is absorptivity. And from our earlier solution of the equation, we know this quantity is e to the power minus a lambda L, if a lambda is a constant along that length. So, with this we can see that the directional spectral absorptivity of a gas is 1 minus e to the power of a lambda L. A very important result to understand, connect what we learned for solids and liquids to gases. And you can see clearly that in the thick limit, the direct spectral absorbed approaches 1. So, when a lambda L is much greater than 1, alpha prime lambda approaches 1, and when a lambda L is very, very small, alpha prime lambda is equal to a lambda L. So, this is a very important result, that in the thick limit all gases, their directional spectral absorbed approaches unity, and in thin limit it is very small, equivalent to a lambda L. If a lambda L is very, very small, it approaches 0. Now, notice that we already mentioned that a lambda is a very, very complex and rapid variation with lambda, which means alpha prime lambda is even more rapid variation. So, let me now plot for a typical situation. Alpha prime lambda has to be only between 1 and 0 because of this definition here. So, there are many gases that we encounter. It will go from almost transparent alpha prime lambda 0 to 1 over a very short distance. So, this is the complexity that we face, that this quantity will fluctuate between 1 and 0 over a very short distance along the wavelength direction. So, most of the difficulties that one has faced in solving problems in radiative heat transfer has been on account of the rapid variation of the directional spectral absorptivity with wavelength. This is a problem which people have been struggling to handle for the last 100 years. Today, the main advantage we have is an access to a high speed computer, which enables us to do large number of computations every second. So, today the complexity introduced by this large variation of directional spectral absorptivity with wavelength is mostly handled by solving this problem on the computer. That we will take up later. So, right now we want to look at simpler issues in front of us, so that we understand the nature of this equation that we have to solve, and later we will talk about what are the actual ways to tackle this problem. Now, in the discussion so far, we have only talked about absorption. We neglected scattering without absorption. Remember, a gas which absorbs will also emit. How about emission? So, when you are going along a path, there is a decrease in the intensity on account of the absorption by the gas. This is this quantity, but there must also be an increase in the number of photons due to emission of the gas along that direction. So, gas emits radiation along the direction in which you are interested, and that depends upon the emissivity of the gas. So, from the basic definition of emissivity which we began in the first few lectures, we know it has to be this quantity. Notice the B here. So, the amount of emission in a given layer dx is the emissivity of that layer times the black body intensity at the temperature of the gas. Okay. So, this follows from the definition of emissivity. Now, we invoke Kirchhoff's law and say from Kirchhoff's law, alpha prime lambda equals epsilon prime lambda. It's always true as long as you satisfy a condition called the local thermodynamic equilibrium. So, this is a powerful result from Kirchhoff's law. So, you substitute that there. So, we get the statement that change in intensity is equal to a decrease on account of absorption and an increase on account of emission. And we made this equal to absorptivity. So, from the previous discussion, this is 1 minus e to the minus a lambda dx, the absorptivity equals emissivity. Yeah, the dx will come later. So, if you take the length dx to be small, dx is quantity you have chosen, we can keep it as small as possible, and as dx tends to 0, this will become one plus for small a lambda dx. This is nothing but 1 plus a lambda dx, 1 will cancel out, you have this equation. So, finally, we have equation for change in intensity due to both absorption and emission by the gases as so, this is the most important equation for a non-scattering medium, non-scattering gas, which says that the change in intensity along the path is equal to the absorption coefficient times the difference in intensity between the intensity of black body emission along the direction at the temperature of the gas minus the incoming intensity. So, notice the difference. One of them contains a subscript b, which you can calculate from Planck's equation. The other one is whatever intensity is coming in to the gas. So, let me visually portray that for you. Here is a surface from which this is coming, and here is the layer of interest to you dx. So, this layer emits radiation, and that radiation emission is a lambda dx I prime lambda b at the layer temperature. Well, this is nothing but I prime lambda from the surface. So, this intensity will change as it goes through the gas. It will decrease because of absorption, and increase because of emission. Okay. So, that is the main information that you get. So, let me again write this as an ODE. So, this ODE is somewhat more complicated than the one we looked at earlier. We have now a non-homogeneous term. This is not a function of this. This is an independent parameter which can be determined once the temperature of the gas is known. So, this kind of problem you must have solved in your first course in differential equations. So, we know that the answer will come out as I prime lambda x is equal to the first term which involves this, which involves attenuation, and the second term which involves the non-homogeneous term. This is a dummy variable here. This is solution to that equation. Okay. Now, this is a very important equation which will keep coming again and again. So, it is important that you fully understand what this equation implies. So, let me then again draw a schematic to get you to. So, this is a layer at a distance x and x plus dx, and there is another layer also you have to worry about. X delta and x delta plus dx delta. So, the radiation coming here is radiation coming from this surface actually we do not need this line right now, e to the power minus a lambda into x. So, radiation emitted from this surface I prime lambda 0 reaches the plane x after attenuation through the gas, plus emission by all these are gas elements here, all these gas elements will emit radiation in the direction reach here. So, those gas elements will emit this much radiation. And the dx delta this layer, and you have to integrate for all gas elements from 0 to x and take care of their attenuation. So, this is the attenuation term. And this is the emission term. The emission term is an integral, and let me just make sure that I forgot a lambda here. So, this is an attenuation term, this is the decrease in intensity due to the absorption of the gas. The next term is emission by all gas elements between 0 and x, which reach x, and so this is the black body emission, this is emissivity of that layer, this layer, and this is the attenuation which depends on the distance between this point and this point. Okay. So, we are able to express the intensity at location x in terms of what started from a surface 0 after attenuation through the gas and arrived at x. The next one is summation of all emissions from all layers between 0 and x and their attenuation depending on the location of the gas layer with reference to this plane x. So, this is a very important result which we will see many times, and one must clearly recognize the general form of the equation, but there are a few approximations which will help us. Suppose you have a cold gas, gas temperature is very, very low, then this quantity will be very small, emission by the gas. So, we neglect the second term, then we have very simple approximation for attenuation because emission is small. So, this may be relevant in some situation where the gas temperature is very small compared to the temperature of the solid surface here, and imagine there is a hot ball of furnace emitting to a cold gas, in which case the emission term is small, only the absorption term plays the role. The other extreme is, suppose you are in the interior of a very large medium, extremely large medium, so that the surface 0 and surface L are very far away, then the intensity that you see will be dominated by the emission term. So, in the interior, far away from the walls, you might be able to only represent the intensity by this kind, provided of course, A lambda is large. Now, we want to make this result little more general. See, remember this result was obtained assuming A lambda is a constant. Independent of space. Now, this is not true. The absorption coefficient A lambda is a function of space. If you ask why, you can from basic physical background can argue that this coefficient depends upon the concentration of the gas of the ice species, depends on temperature, depends on also total pressure. So, if along a certain path the temperature is varying, pressure is varying, the concentration of the gas are varying, then this will not be a constant. So, if A lambda is a function of x and not a constant, you have to redo your calculation to allow for the fact that the absorption coefficient varies along the path in which your ray is traveling. When that is happening, it is good to define another quantity called kappa lambda, which is 0 to x A lambda with the dummy variable. Now, this is a non-dimensional quantity and is normally called the optical depth. So, it is a very convenient parameter, or actually in this case variable, because this will be a function of x, note. So, you can redo your integration and easily derive that the intensity of the gas at a certain location kappa lambda is equal to I prime lambda 0 e to the power minus kappa lambda plus 0 to kappa lambda I prime lambda b of kappa lambda tilde, a dummy variable, e to the power minus kappa lambda minus kappa lambda d kappa lambda tilde. So, this is a general equation when the absorption coefficient of the gas is a function of the path along which you are traveling. So, you define a quantity in terms of the non-dimensional optical depth. So, we have implicitly accounted for the variation absorption coefficient with temperature, pressure and concentration. So, this is the result which will be basis of all our future discussions, and the advantage of this generalized equation is that we can take care of variations of A lambda with path, because it is built into the definition here, and so this will be the basis for our future calculation. Now, this equation gives you the directional spectral intensity in a given direction. Okay. So, just to give you an example, now let us take up two parallel planes. So, this is a useful tool to understand in any given direction how the intensity is changing. But finally, what you want is not I prime, you want a flux. The flux is obtained after averaging the intensity over all angles theta and phi. Okay. So, if you recall, our definition of radiative flux was nothing but integral over omega of I prime lambda cos theta d omega. If any of you have forgotten, you can go back and look at the definition of I prime lambda, and you will remember a cos theta is built into the definition, and so is the d omega. So, this follows from the definition of I prime lambda in terms of q r lambda. Now, this integration can be tedious, but if you assume gas is a isotropic emitter, then integration is somewhat simplified. In the direction phi, everything is same. So, you integrate and get 2 pi. So, you will get 2 pi 0 to pi I prime lambda cos theta, and write this in terms of sin theta d theta. So, integration phi gives you 2 pi, and then you have to integrate over all angles 0 to pi. So, let me visualize this for you. So, you have a plane and you have to integrate over this and also this. So, integration, if we start with 0 to pi, so it covers in this plane parallel situation all intensity going upwards and downwards. So, once you solve for the directional spectral intensity by solving those equations, you then plug it into this expression to get the flux, and finally, this is what matters, q r lambda and its derivative. Now, the question is, how do you do the integration? Now, for convenience, we will divide the integration in two parts, the upper and the lower. And this becomes necessary because if you look at a layer, the center of the gas here, the radiation going downwards is coming from the upper wall, and radiation going upwards is coming from the lower wall. Okay. So, it makes sense to split this integration 0 to pi as 0 to pi by 2 plus pi by 2 by pi. And the advantage is in the region 0 to pi by 2, if you define mu as cos theta, this is greater than 0 for theta between 0 and pi by 2, while this quantity mu is negative for theta between pi by 2 plus pi. This is our definition. We are assuming that the layer, we draw a normal here, and this is 0 to pi by 2, and this is pi by 2 to pi, this portion. Okay, we go through all these somewhat tedious calculations, and I want you to do it yourself to make sure that you fully understand the mathematics involved. So, our QR lambda becomes 2 pi into 0 to 1 I lambda plus upward going radiation mu d mu minus 0 to minus 1 I plus downward radiation mu d mu. So, here considering all rays moving upwards from the bottom plate to the top plate. In the other case, you are considering all rays moving downwards from the top plate to the bottom plate. So, schematically, the first direction schematically, now let me draw this. So, I have some plane here. So, I lambda plus is intensity that is emerging from this plate to this gas, while I lambda minus is radiation coming through the top surface and top layer of the gas. So, this involves 0 to pi by 2. So, where mu is cos theta. So, when theta is between 0 to pi by 2, this quantity is always positive, and the second one involves the theta value between pi by 2 and pi. So, it will be negative. Now, we can write what is I lambda plus and I lambda minus. Let me first write what is I lambda plus. All intensity going upwards is equal to all intensity going upwards from the bottom surface and e to the power minus kappa lambda by mu, and the second term is so this is very similar to what we have done earlier, only some notation has changed. We have explicitly accounted we are measuring everything with respect to vertical direction, and this mu and this mu is coming in because of the difference between the direct radiation and the slanted radiation. So, all rays which are not travelling perpendicular to the two plates are going to travel longer distance, and hence you have to divide by cos theta. That is the only thing we introduced here in our discussion. Otherwise, this result is very similar to the earlier one. Now, we plug everything into these equations and calculate the upward and downward radiative flux. You do all these integrations, then you will get the upward radiative flux will be equal to, I will write down the expression, explain what these terms are. So, this is an important result after integration over all angles. Notice that there are two terms, and B lambda 1 by definition is pi times I plus lambda 0. So, this is the upward travelling intensity from the lower surface, and which is assumed to be diffuse isotropic. And so, pi times that is radiosity, the radiation leaving the surface. This is radiosity, and the second term of course is the emission term, which has not really changed that much. So, that is QR lambda plus upward going radiation. Then you come to downward coming radiation, which is coming at the top. This will have the radiation from the top surface times the distance is the highest optical depth, K lambda 0. So, the second equation right now here is the radiation leaving surface 2 at the top going downwards after attenuation through all angles. The second term is gas radiation emitted downwards integrated over all angles, taking into account the different attenuation of the ray depending on the angle. So, angle plays a very important role here, and so we will now illustrate this. Net flux is up minus down. So, the final expression for radiative flux, which we will be using quite frequently in the next few lectures, is written as follows: the net radiative flux between lambda and lambda plus d lambda has the radiosity of the top surface, or in this case bottom surface, E2 of kappa lambda I am sorry, I have not defined the functions E3 and E2. Let me do that first. That exponential integral function has to be defined before we go further. And let me do that now before we get on to this. I should define the E2. Let me see, can I define E2 anywhere here? No, E2 had to be defined here. Let me define here. What is E2 of x? Nothing but 0 to 1 mu to the power of n minus 2 e to the power of minus x by mu d mu. So, this is E n of x. This is called the exponential integral function and plays a fundamental role in radiative transfer. It accounts for essentially angular integration. So, you are getting E3 and E2 both here, and you go to the next page. This has to be E3 and then we will put a negative term here, which is 2 B2 lambda, the bottom surface, this is top surface. So, let us put this as 1 and this as 2. So, the radiation from the below goes up, radiation from above comes down. So, it is negative flux, and the distance travelled here is this, where k lambda 0 is equal to 0 to L a lambda dx, the full optical depth of the medium. And there are two more terms. One, all gas radiation emitted from the bottom surface, from the bottom layer, this is the radiation emitted by all gas elements lying in this region, and of course, the region above, both are there. So, that will emit upward, that is positive. Then minus 2, this has to be 2, I am sorry, 2. This is integration from kappa lambda 0 to kappa lambda 0 E lambda b E2 of kappa lambda tilde minus kappa lambda d kappa lambda tilde. So, this expression for radiative flux must be properly understood. The first term is emission from the photons from the or photons leaving the surface 1 and on attenuation reaching the point of interest to us, and this attenuation term takes account angular distribution of photons, or not all photons are coming vertically, some of them coming at an angle, and you are integrating all angles. That is upward flux. Then the downward flux is the radiation leaving the top surface and traveling the distance travel now is counted, because everything is counted. This is x going upwards, this is 0, this is kappa lambda 0. So, when you come to this point, your travel distance kappa lambda 0 minus kappa lambda, that is attenuation. So, that is the downward flux from the top surface. Then these are emission by the gas elements between 0 and kappa lambda, which reach the surface, and finally, emission from all gas elements above this. So, let me show this schematically. So, this is one term, first term in the equation, surface 1, surface 2. Second term in the equation is from this surface coming here. This is zero and this is kappa lambda 0, and I am sorry, this is 2 and this is 1, and this is now element 2, this is element 1 equal. And the third element is emission from gas layers here, which comes here, that is the third element, and fourth element is gas layer here emitting radiation here. So, you must fully understand the role played by these four streams. Stream 1 is the radiation leaving surface 1 either by emission or reflection, and after attenuation, which is angle dependent integration, reaches this layer which is kappa lambda. The second term is radiation leaving the top surface coming down to the level kappa lambda, and hence it travels the distance kappa lambda 0 minus kappa lambda to reach here. And the two other terms are radiation emitted by all layers from kappa lambda tilde to kappa lambda tilde plus d kappa lambda tilde, this layer, and integrate all emissions from surface to kappa lambda to get the third term. And the fourth term is radiation emitted downwards by all gas layers lying above kappa lambda, and so they travel distance kappa lambda minus kappa lambda tilde, which is built into the exponential integral function. So, these four terms contribute to the flux. The net flux at any layer is the addition and of all these four terms, and by our notation, radiation moving downwards is positive, radiation moving upwards is negative. That is why terms 2 and 3, which are terms coming down, are negative, while terms 1 and 3, which are terms going upwards, is positive. So, we have at last got an equation, and this geometry we used is called the plane parallel model or atmosphere. So, this is the simplest formulation of radiation problems. It is essentially 1D model. We do not account for variations in y and in z, we only worry about variations in x. So, this is an approximation which is all right as long as the distance between the plates is large compared to the length of the plates, in which case we can neglect what is happening in the ends. So, we have a simple plane parallel model. So, this works quite well in many situations, but if you have a, for example, a cubical enclosure with gas in it, then this is not a good approximation. This is a cubical enclosure with gas, and here the plane parallel model may not work well, because the gas inside this cubical box is getting radiation from all the 6 surface of the cube, and so you have to go for the full 3D formulation for this case. That is fairly complicated and hence cannot be easily done anything in the class. So, we will stick to a simple one dimensional model of the plane parallel atmosphere to illustrate all the basic issues in radiation transfer, and we presume that you know that if you have to deal with 3D model, it is similar to 2D model, except that there is more complexity and computation involved, which can be tackled in the real world, but we will be using only the 1D model for teaching purposes. Thank you.